इन लोगों ने बोला वीडियो बंद करो, इन लोगों ने वीडियो ऑडियो बंद થઈ જશે
ના વિડિયો એટલો બંધ
એ લોકોનું
લોકોનો તો બંધ
Can you hear? Good morning, Kripal. Surabhi. Okay. Today is the last class in this topic. So I'll take 5-10 minutes more. Lastly, there are certain things which are good to know. If time permits, I'll take, otherwise I'll leave the slides with you. Last class, we had seen each of the waves. Their recording consists of waves, durations, segments. Each wave has a duration and voltage also. Segments and intervals. We have seen what importance of P wave, QRS complexes, T wave, PR interval, QT interval. We also looked at how heart rate can be determined using the RR interval. I think we stopped at this slide. If you have 15 millimeter deviations between two R peaks, the heart rate is around 300. If you have 25 deviations between two R peaks, the heart rate is around 60. So 1500 divided by number of small deviations between two R peaks gives you the heart rate. I also told you that if the rate is irregular, you can determine the rate. Normally we talk about it in practicals. I'm not sure I will be taking the practicals. Somebody else will be taking. So in brief, I'll just tell you here itself that if the rate is irregular, then how will you determine the rate? If the rate is irregular, then you need to get a long strip, a 10-second strip or a 6-second strip. Like for example, this is a 6-second strip. The strip you see here is a 6-second strip, or a little more than 6 seconds. 6 second, 25 millimeter per second is the chart speed. Okay, so if it's a 10-second strip, means a 25 millimeters strip, 10 centimeter strip. Or you take a 6-second strip. So then you take a 6-second strip. Let us say 6 seconds means from this point here. Let me get a pointer. Let's say from here to this point. This might be around 6 seconds. Then find how many peaks are there between this second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say there are 10 peaks in this 6-second strip. 6 seconds means 60 seconds is the per rate. So 6 seconds into, let us 6 into 10 is 60 seconds. So if you have 10 peaks, 10 into 10, 100 is the rate. So similarly, in the above you can calculate. Take a 6-second strip. The number of peaks into 10 will give you the heart rate. If you take a 10-second strip, number of peaks or peaks in that 10-second strip into 6 will give you the heart rate. If the rhythm is irregular, to find the rate, you take a 10-second strip, multiply the number of peaks into 6. If it is 6-second strip, multiply it with 10. Clear? Okay. Let's go forward. I told you importance of ECG to determine no abnormalities of rhythm, conduction defects. In conduction defects, you have, it might be a sinusoidal block, or it might be an AV block, or it can be a bundle branch block. SA block, or it's just a strong, it can be due to a dysfunction at the SA node, or it can be due to strong vagal stimulation, or due to some drugs. Then what happens is the new rhythm of the ventricles will be due to the AV node. So you have an AV rhythm, nodal rhythm. You have a nodal rhythm. Here what you find is the PR interval might be shortened, P wave might be absent, QRS complex and followed by T wave. T wave might have inversion, or T waves might be slowed. P wave, it is seen, it may be inverted because retrograde conduction is occurring, or it can be absent also. And P wave might be seen sometimes after QRS complex. Important is that PR interval duration will be reduced. Atrioventricular block, it may be a partial block or a complete block. If it's a partial block, it can be first degree block or second degree block. In the first degree block, last class we already seen this part, PR interval is prolonged. Here it's an SA for P wave followed by QRS complex followed by T wave. It's a sinus rhythm, but PR interval is prolonged. Okay, it might be due to slowed conduction at AV node or bundle of phase or bundle branches. Here, the first degree block, the PR interval is only prolonged. There is no drop beat. Conduction might be delayed. Conduction might be due to conditions like ischemia or hypokalemia. It may be normal or it can be prolonged. It can be type 1 block or type 2 block. We'll see one example here. Like for example, in the second degree block, Wenckeblatt's block, PR interval is gradually increasing. If you look at this one, the next, PR interval is gradually increasing, and then one ventricular event is dropped. There's a drop here. So there is a progressive increase and one QRS complex is dropped. So drop beat. This type of block is called as second degree block. There is a gradual increase in PR interval and gradual lengthening of this PR interval, and then there's a drop beat. It's called as Wenckeblatt type block or Mobitz type 1. Mobitz type 2 block is you have a normal PR interval. There's a drop beats. 1, 2. There's a drop. P waves are seen, but it is not conducted further. So there's a 2:2 block or 3:1 block. After this is a normal PR interval, then there's one P wave, there's a drop. There is 3 normal, then there's a drop, 3:1. So QRS duration might be prolonged here in this condition. Like for example, here the QRS duration is prolonged. This type of block is called as Mobitz type 2 block. Now next is mean electrical axis. Now mean electrical axis, whenever we talk about mean electrical axis, what it means is mean QRS vector. You must have studied when we talk about vector diagrams. You have many instantaneous vectors and a resultant vector is drawn. Similarly, these are the green ones are the instantaneous vector. the resultant vector is this. The mean electrical axis, the mean QRS vector for a ventricle axis. Because ventricle event is a major event. So whenever we talk about the mean electrical axis, we are talking about mean QRS vector or mean electrical axis of the heart. So mean electrical axis represents sum of all the individual vectors drawn in instantaneous vectors. Normal mean electrical axis is considered minus 59 degrees or ranging from minus 30 to plus 110 degrees. Actually tells you about mean electrical vector. If you remember the influence triangle, I told you if you know the electrical events of any two leads, you can know the event of the third lead. The normal mean electrical axis ranges from minus 30 to plus 110 degree electrical axis. Axis of minus 30 to minus 90 is called as left axis deviation. From minus 30 to minus 90 is left axis deviation. 110 to plus 180 is right axis deviation. This is your hexaxial reference system. If you remember your hexaxial reference system, you come to the next slide. Your lead 1 is 60 degrees, lead 3 is 120 degrees. AVF is 90, AVR is right axis deviation is from 180 degrees. Left axis deviation is from minus 30 to minus 90. Indeterminate axis is minus 90 to 150 degrees. The hexaxial reference system. Now this axis, mean electrical axis, when we're talking about mean electrical axis in the frontal plane. If lead 1 QRS complexes are in the positive direction, the axis is normal axis 30 to plus 110 degrees. Or plus 100 degrees. Some books write it as plus 100 degrees. Now, this is a shortcut way of finding an axis. There are many methods in which you can find, say the axis is left axis deviation or right axis deviation. First, let us look at the correct method. We'll come back to this slide again. Why it is not? Okay. I think that slide is there in the right bundle branch blocks condition. To find the axis, you have to find the net QRS amplitude. When we do, we'll come back to this slide again. Let me finish bundle branch block. I'll come back to this. Now, left axis deviation is seen in conditions where if there's left inferior wall MI, left anterofascicular block, left ventricular hypertrophy, some cases of left bundle branch block, left axis deviation. Now, if you see here, in lead 1, you have positive QRS complex. In lead 3, there's negative QRS complex. So they are opposite. This previous slide, lead 2 is positive, lead 3 is positive or negative. In left axis deviation, if lead 2 is negative, lead 1 is positive and lead 3 is negative. If lead 1 is positive, lead 2. Lead 1 is positive, lead 3 is negative, they are leaving each other. Left. If you draw any axis, you can say where this is. If you say lead 2, you draw perpendicular to lead 2, and if your deflection is positive or negative, if it is positive, it will be within this. It can be normal axis or but if in lead 2 it is negative, in this half. So mostly if lead 2 is negative, then you have a left axis deviation. And if lead 1 is positive and lead 3 is negative, which is lead 3, this is your lead 3. You draw a perpendicular here, then if lead 1 is positive and lead 3 is negative, then your axis is here. Right axis deviation, lead 1 is mostly, it can be negative, and it can be seen in left posterior fascicular block, anterolateral wall MI, some cases of right ventral branch block. Normally it can be normal in some children and teenagers. Here in right axis deviation, lead 1 is negative, and to keep lead 1 and lead 3 together, they are like reaching each other. So reaching is right, that is the way lead, this is lead 1, draw a perpendicular to this. So you have a positive half and negative half. So if lead 1 is negative, the axis is here, this half. Okay. Draw perpendicular here, the axis is in this half. If lead 3 is positive, so the axis is here. So usually it will be right axis deviation. The bundle branch block is another condition where what happens is you have right ventral branch and left ventral branch. So if there's a block in either right ventral branch or left ventral branch or the septal branch or fascicular, conduction path will be affected. So the whole, let's take an example. Suppose this is a right ventral branch. If suppose this block is not there, then the normal conduction will be occurring from here, it will be occurring here, both left side and right side together. But as there's a block here, what happens is it is not conducting through this right bundle branch. What happens is this septal activation is taking, then this spread will occur in this direction. So because it is taking a totally different path, the ventricular muscle is continuity is there, practical continuity is there. So the depolarization will spread from this ventricular muscle to this direction. So there is total spread of activity will change. It's like this. Like you have, let's say you are going from college, you want to go to Anand. Path you can take. You can take directly the main highway, go to Ganesh Chowkadi, then go to Anand railway station through Amul Dairy Road, straight path. Or if the road is blocked, you might take a path from inside Vidyanagar and take a totally different route to reach the Anand station. So each of these routes will take more time, and you are taking a different direction. So result is the electrical vector directions will change. The instantaneous vector directions will change. So the mean electrical vector direction will change. One, the mean electrical axis will change. Second, this deflection, the kind of deflection which you see in the leads, particularly in the V1 to V6 leads, will change. Third, the duration for conduction of impulses, that means the QRS duration will change. Okay, so what you see changes will change. You will see QRS duration when be greater than 0.12 second. You might see changes in the progression of QRS complex from V1 to V6. So wide S wave in lead 1, V5, V6. You will find a kind of tall R1 in V1 and QRS duration, whatever right axis deviation. You have this block here. Then the conduction to this right vent here will occur from the ventricle. You have R waves here, R prime and R1 here. Now coming to the correct method of determining axis. Now, this is, you, like for example, in this case, you take two axes, let's say lead 1 and lead 3. Find the net QRS amplitude between in lead 1 and lead 3. Net QRS amplitude with number of positive deflections minus the number of negative deflection. Suppose in lead 1, the number of negative deflection here is, let's say, about 6. Around 8. 8 is a net negative deflection. So you plot in this graph. Then in lead, number of positive deflection minus number of negative deflection, net QRS. So number of positive deflection, let's say 15, 20, 23, 23 minus 3, let's say 20. So plot 20 here. Draw perpendicular to lead 1, draw perpendicular to lead 3. Where the point meets, from the point you draw it back to the center here. This is your axis. Okay, that becomes your axis. If it's a normal axis, you find the net QRS amplitude, plot in lead 1 and or you plot in lead 1 and lead AVF. AVF also you can plot. AVF is 90 degrees. And you can find out what is the axis. Left bundle branch block. Similarly, in left bundle branch block, there's a block in the left bundle branch. Conduction will occur from the right ventricles towards the left ventricles. So the whole instantaneous vectors will change. The whole spread of activity will change. So what you'll find, wide S wave in V1 and V2, wide R waves in V1, the QRS duration will be also prolonged. V5 and V6 there is a wide S wave, there will be R wave and an R prime. Notched R wave they will call it as. Like for example here, we plot the net QRS amplitude in lead 3. Similarly for lead 1, draw perpendiculars from the point of intersection, trace it back to the origin. This is your axis. This angle is your axis. This is the correct method of finding the axis. Now, in ventricular hypertrophy, what happens? Just a minute, excuse me. It is a ventricular hypertrophy. Hypertrophy will occur if there is a particular muscle that has been working at a resistance for a longer duration. A muscle hypertrophies. In normal case, if this is your recording leads, if the electrical activity is moving away from the recording lead, your downward deflection. The electrical activity is moving towards the recording lead, your upward deflection. If there is a hypertrophied muscle, potential, the electrical vector, the length of electrical vector will increase. So potential will increase, the amplitude of that wave will increase. Second change we can see will be the duration. The duration will also increase. The duration of conduction will increase. So this duration will also increase. So just a left ventricular hypertrophy, this is hypertension. In case of hypertension, what happens is you can see a left axis deviation has taken place. Lead 1 is positive, lead 3 is negative. Top, you will have a left axis deviation. What about V2 and V5? The tall R waves, deep S wave. There might be changes seen in T wave also. T wave inversion might be seen sometimes. Repolarization process also. If it's the right ventricular hypertrophy, due to pulmonary hypertension also. In lead 1 and lead 3, lead 1 there is a deep S wave, R wave, tall R waves in lead 3. Trace it into the lead 1 and lead 3, drop perpendicular, trace it back, the origin, you get an axis. In all R waves, and V5 there is a deep S wave. Now another condition where you might see abnormality in ECG, a premature beat or an abnormal focus. I told you the electrical activity generated as conducted through all the branches, through internal branches, HDAV junction, Purkinje fibers, bundle of these bundle branches, Purkinje. So normally the specialized conducting tissues are the only ones who are generating. But sometimes there can be, this is a muscle also has a property of irritability. There can be an abnormal focus which can get excited in the muscle. It can be due to small pathological variation which might be generating just one impulse, causing one beat. That abnormal focus can be anywhere in the atrial musculature or in the ventricular musculature. Or it can give you a paroxysmal impulse. So, suppose the abnormal focus in the atria, and before the SNOD impulse is generated and conducted, this impulse is conducted through. It can lead to, and if it is giving just a single beat, it will give you rise to a single ectopic beat. This ectopic focus is in the atria, it will give you atrial ectopic beat. Or it can give you, okay, another important thing here is, because of this beat, the next beat is occurring after a long duration. It has given only one single impulse. The next beat is after a small pause. It's called as a compensatory pause. Here there's a compensatory pause. It's compensatory pauses. This is the ectopic beat. The next beat is occurring after a compensatory pause. Can you tell me why this is occurring? Would you like to put it in chat? Why this compensatory pause might be seen? You see, what happens is this beat has passed through and during this, when the normal impulse from SC node was supposed to enter, it was not able to enter. The next beat, which is normal beat, which was supposed to enter, during that period, in a refractory period, due to this ectopic beat. Hence, the normal impulse is not able to pass through. So after this pause, when the muscles are available for activation, the next normal beat is able to pass through. Because of the refractory period, this compensatory pause is seen. It's good to know. Nobody will ask you in exams, but is generating many impulses and it is conducted, you will find a kind of repetitive rapid rate of conduction, a kind of tachycardia will be seen. The atrial tachycardia can be seen. Sometimes this ectopic focus is generating impulses at rate more than 160 to 220. 1:1 conduction is occurring. Or there might be a physiological block due to the refractory period of AV node. You will find an atrial tachycardia. Or if the rate is much higher, it might lead to an atrial flutter, and where you'll find after every 2 or 3 P waves, you find one QRS component. One is passed through. So this is called as a sawtooth pattern. In case of atrial. I'll jump through these things quite far because not much important. Nobody will be asking you. We'll be studying about it in more detail later on in the second, third year also. Now, an ectopic focus can be also be there in the ventricles. If it is there in the ventricles, then what happens is this impulse is conducted through. You might find before the normal one, you have an ventricular complex rising. There may not be a P wave. There will not be a P wave before this ventricular firing. I'll come back to this. Okay, if that rate is this came in between atrial flutter, that was 220 to 300. Sometimes this, if the rate goes much higher, the muscles, there might be a fibrillation occurring. The P wave may not be very discernible. Atrial fibrillation might be seen, may not be very clearly seen. The conduction will be very haphazard, and atrial fibrillation might be seen. This, if there's an atrial extrasystole, then similar to ventricular extrasystole, if there's an ectopic focus which is generating impulses, it will lead to a premature ventricular beat. If there's a premature ventricular beat, here also you will find the next beat, normal beat is dropped, so there will be a compensatory pause. Single impulse is generated. The QRS duration will be prolonged. The direction of conduction will be altered. So you'll find the QRS complex also might be different. The repolarization will be affected. So T wave inversion will be also seen. Yeah. So this is an ectopic beat occurring. A premature ventricular contraction occurring. Compensatory pause is occurring because of what we call it as refractory period of this ectopic beat. If the ectopic focus is generating many impulses at the time, about 140 to 220 or so, then you will find a paroxysmal beats occurring. Many beats are continuously generated. It's a serious condition which can lead to a ventricular fibrillation. It can lead to a ventricular fibrillation. That is, when this many impulses generated at a time, there's not coordinated contractions are not taking place. And it can lead to ventricular fibrillation. They call it called a re-entry phenomenon. Now, what is this re-entry phenomenon? Because of this re-entry phenomena, it can lead to an uncoordinated contraction. And there is not a coordinated contractions are ongoing. Every regions are contracting in a different times. So it's like just a wavelets occurring. And it is a dangerous condition, and it can lead to a failure, heart failure. Now, what is this re-entry phenomenon? Please understand this re-entry phenomenon. I actually would like to draw this, but this is not the diagram which I am right now. Let's say you have a circular muscle. It's a circular muscle. And at a point, I draw. I need something. Okay. Okay. Oh, I have pointer pen also. Suppose there is a point where, let us say, there's a stimulus, position is spreading, and it is spreading in this direction and coming back here. Okay. Now this depolarization cannot enter back into this point. Why? Please. Are you there? Let's say you have stimulated this muscle here and the depolarization is spreading in this direction. And this depolarization will come back to this point, but it is not able to again enter. Why? In the absolute refractory period. Okay. Because this region is in absolute refractory period, it cannot enter. Now, if you want this impulse to re-enter again, to occur, the re-entry to occur again, what are the conditions in which it can re-enter? Can you list down the conditions? This impulse you have stimulated at this point, and it is spreading in this direction and reached back to the point of origin. It is not able to re-enter because this region is in absolute refractory period. Now, if we want this impulse to re-enter at this point, in which conditions this impulse can re-enter? If this one, if this, let us say, become very, the length has increased. One. Second condition is the conduction has slowed. The length has increased. By the time it reaches to this point must have repolarized and is available for re-entry. Second, if the conduction is slowed. If the conduction is slowed, by the time it reaches to this point again, it will re-enter. It has become repolarized. It will re-enter. Re-stimulation can occur. Third, if the refractory period is shortened, in that condition also it can re-enter. Okay. So if three such conditions are occurring, then it can re-enter. Suppose. So if the re-entry is occurring in normal conditions, muscle is going, this impulse is arise from here, it's conducted in this direction, conducted in this direction, conducted in this direction. It's not able to re-enter because this region is in refractory period. But if suppose this region, it is conducted like this, and this region has repolarized, the two has repolarized. It is available for activation when this three impulse is coming back. So it will enter here. It will enter through here. So by the time it reaches here, this place has become repolarized. It will again enter. So this will lead to a kind of re-entry occurring. And this re-entry process, if it occurs in the muscles, then it can lead to a fibrillation condition. Go back to the slide. So re-entry phenomena can be seen in long pathways when they're dilated, or if the decrease in conduction occurring, blockage of Purkinje system or ischemia, or due to high level of potassium ions, or shortened refractory periods due to epinephrine or repeated electrical stimulations. So if there's a re-entry phenomena occurring, this re-entry phenomena can lead to arrhythmias. And for re-entry phenomena which are available to activation. So, I remember I told you that remember the T wave, the peak of T wave. If you remember that, compare the T wave with the action potential, cardiac action potential. The peak of T wave almost corresponds with the center part of the repolarization wave. You have your cardiac action potential like this. The peak of T wave is a kind of vulnerable point. Some of the regions are depolarized, some are repolarized. So those, because some regions of cardiac muscles will be repolarized, some are depolarized. At that point, if you have kind of a stimulus which can cause a re-entry phenomena can occur. Now, another important concept which I want you to understand is nobody else will tell you about these things later on. Just it's good to know current of injury. Now, any muscle which is an ischemic or infarcted muscle, that region is always depolarized or always electronegative. In the first class, I told you the electrical vector always points from negative to positive. So suppose this is the ventricles. The whole ventricle is repolarized, but this region of the muscle is sort of injured due to ischemia or infarction, whatever reason. It is depolarized. It is negative. So that means the electrical vector will from negative to positive. So there will be a kind of electrical vector pointing from this negative region to the positive region. This electrical vector, due to this injured region occurring, is called as what we call as a current of injury. The flow of current from the injured region to the healthy region is what we call as the current of injury. Now, why it is important to understand this? Okay, we come back to this. Now, J point is the end of QRS complex, just beginning of the ST segment. It is a isoelectric point, zero current point. Okay, just remember this J point is important to determine the current of injury. So this figure is from Guyton. Suppose there is a region which is injured. Because of this injured region, there is a negative end. The whole region is repolarized. You have a current of injury flowing in this direction. Now, when the ventricular activation is taking place and the whole ventricle is depolarizing, what will happen is the ventricular depolarization vectors of change will be affected due to this current of injury. So you will find this current of injury is also affecting it. So the overall electrical vector will change. Now, if you want to see the change in current of injury, because of this change in current of injury, where it is occurring. Now, you can also find these vectors if you put it in this graph, like we found the electrical axis. You can find where is the location of that current of injury. You plot those in this. See, this is the vectors. This is the deflections which has occurred. Okay. Now this is the current of injury in case of, let's say, lead 3, and you have lead 1. Okay. You draw it to this. This is in lead 2. Sorry, this is in lead 2, and let's say in lead, any of these two you take. Lead 1 and lead 2 you draw and draw perpendiculars. You can get the current of injury. The negative end will point to the location of the injury. For example, in this ECG figure, there is a J point. and this is the negative deflection occurring due to current of injury in lead 1 and lead 3. You can draw it on the axis and draw perpendicular, trace it back, and place it on the part, the point of origin, the location of where the is a negative deflection. We got negative current of injury, and there's a positive current of injury. This is also taken from Guyton, and draw it negative and positive, draw perpendicular, just trace it back, the positive end of the injury potential towards the negative. The negative end will point the injured region of the muscle is located, the abnormal portion of the heart, from where the current of injury is emitting. If these are certain abnormalities which in ECG you might see, if QRS amplitude, if Q wave is 1/3 of that of QRS amplitude, it's an abnormality. If Q wave is quite wide, it will be considered abnormal. Significant changes in Q wave seen in necrosis. ST elevations might be seen in case of there's an injury, or T wave inversion. That means repolarization is affected in some case of ischemia. It will be seen. If this ST segment changes or is seen in V3 to V6, V3 or V6, it is the current of injury might be located at is in the posterior region. AVF 2, 3, it is in inferior regions. If it is in lead 1, AVL, V5, V6, lateral left ventricle regions. These are good to know, but is not needed for you in your first year. Now, if there is a re-entry phenomena occurring in the mid portion of the ventricular fibrillation, an uncoordinated contraction is occurring, it can lead to death of the individual also. It can lead to an asystole. Last class, I think somebody asked me in the chat box, I just remember, when I looked at this graph, I remember this, about long QT, why there is what was the question? Increase in heart rate after a long QT. After a long QT, sometimes there might be a increase in heart rate. There also one of the main reasons I think is because of the re-entry phenomena occurring. There will be uncoordinated contraction. There will be a kind of increase in heart rate. There can be similar conditions. Kind of conditions. You might have to give a defibrillation. So normally a DC shock is given, an automatic external defibrillator is applied. Now, why you do need to give? Happens is you send the whole of the ventricle into a total depolarized state. Then you are giving the SA node a chance to take over the heart. even the normal regions, the abnormal regions, they are all gone into depolarization. Now, if the SA node is able to take over it SA node an opportunity to take over the heart and generate impulses and conduct it normally. Okay, I think I will stop here. There are a few more slides that you can go through on your own. They are good to know. Stop. I'll send the slides to you in the next, maybe by evening I will send it to you.